So we're going to talk today about metal semiconductor junctions. We're going to wrap up the semiconductor junctions module. We spent the whole module talking about PN junctions, and now we're going to start talking about metal semiconductor junctions. So let's just jump ahead here. All right. So far, we've looked at exclusively at PN junctions. That's what happens when you put a P and an N-type semiconductor next to each other. And in our clean room lab, you saw how a diode is fabricated, you saw how to test it, and you actually see the forward bias and reverse bias characteristics that we've seen in class actually ends up in practice as well. So there's another type of junction which happens very commonly in semiconductor devices, and this is what happens if you take a metal and you put it next to a semiconductor. All right, there's two possibilities. When you put a metal next to a semiconductor, you can end up creating a diode, actually. This is something that you wouldn't think is intuitive. You'd think that if you just put a metal onto a semiconductor, then you just get a contact into the semiconductor, right? Well, it turns out a metal semiconductor junction can also behave as a diode in some cases. And that's called a Schottky barrier diode. In other cases, it does behave as an ohmic contact, so it just has a contact resistance. This is the type of contact you want if you just want to make an electrical connection to the semiconductor. In other cases, you may intentionally design a Schottky barrier diode because you want to create a diode-like characteristic with just a metal semiconductor junction. So these two things can happen. We'll look at how they're going to happen today. And I'm going to move through these things relatively quickly since we've talked about PN junctions already, and you already have an idea of energy band diagrams. But if I'm going too fast, feel free to slow me down. I would like to get through some of this today and start getting into the next topic, which is MOSFETs. The first important concept is the concept of a work function. Okay. The reason we need to understand the work function is because we'll see that it's important in drawing the energy band diagrams for a metal semiconductor junction. So a work function is a physical number that depends on the type of metal that you have. Or this applies to semiconductors as well. So suppose a metal or a semiconductor is bombarded with energy. So for example, in the form of light. So just as shown in this diagram here, we have light coming in, and the energy of that light is equal to H times V. Now remember, in some of these diagrams, V refers to the frequency of light. Okay, so this V actually represents frequency. Okay, so the energy required for the electron to escape from the solid material into the vacuum is equal to Q phi, also called the work function. So if we think about, jump ahead here and then we'll come back to this. If we look at this diagram here, okay, this is the energy band diagram for a metal. This is the energy band diagram for a semiconductor. We draw those energy band diagrams to represent what all the different energy states are. Electrons can occupy certain energy states. In a metal, those energy states are clustered into a band, and the Fermi level is in the middle of that band. In a semiconductor, there's often multiple bands, and the semiconductor is in between those two of those bands. Okay, these bands represent states that the electron can be in. Okay, they're clusters of states that the electron can be in, and the electron can move from state to state. That's what causes. That's the origin of electricity. Let's go back to this. Now, it is possible to add enough energy into an electron that the electron completely exits the atom. So let me put this into context. If you remember from Module 4, we said that if the light has enough energy, it can cause an electron to go from the valence band to the conduction band, right? That was Module 4. So you guys understand that concept very well. So if the energy is even higher, let's say the energy is very, very high, the electron can attain enough energy to not just go from the valence to the conduction band, but it can attain enough energy to leave the atom entirely. This is called the photoelectric effect. So if you blast a metal with very high energy light, or even a semiconductor, you can actually remove electrons from that material. Electrons will literally come right off. This type of phenomena is actually used in a lot of different types of scientific devices, which we're not going to get into right now. But the focus here is the work function. The work function is the amount of energy required to get an electron to leave the atom. Okay, so it's given in electron volts. This light has to have an energy greater than the work function to eject an electron from the material. This graph here shows the frequency of the light, and this here is showing EM. So this is the energy of the electrons that are emitted. So you'll notice that so there's a way to actually measure the energy of the electrons emitted. We're not going to get into that right now. But if you supply very low energy, low frequency light has low energy. So no electrons are going to be ejected into the material. Once you get to a certain energy, once the energy exceeds the work function, then electrons will start to become ejected from the material. And at that point, the stronger the energy of the light is, the more the energy of the electrons that will be that are ejected from the material. All right, so that's the physical concept of the work function. Now the energy band interpretation, we're going to add to our knowledge or our toolkit of energy band diagrams. So again, if enough energy is added to an electron, it can jump to an energy state, which represents the energy of an electron freed to the vacuum. So this phenomena that we're talking about, ejecting an electron from the material, that can be represented in an energy band diagram by something called E0. E0 is called the free electron level. If an electron goes to that energy state, that represents the fact that the electron is completely removed from the lattice. So this difference between the Fermi level of a metal and the free electron level is given as Q phi m. So this is the energy band diagram for a metal. Now, if you remember back to chapter 3, we talked about the differences between metals, semiconductors, and insulators. We said that a metal has, all three materials have energy bands. They may have multiple energy bands. The location of the Fermi level with respect to the energy band is what determines if a material is a metal, insulator, or semiconductor. In the case of a metal, the Fermi level is usually within the band, somewhere within one of the energy bands. In the case of a semiconductor, the Fermi level is in between two energy bands, and the spacing between those energy bands is small. In the case of an insulator, there's a large spacing between the energy bands, and the Fermi level is somewhere within that spacing. Now, you can go back to Module 3 if you want to look up more on that. But we're interested in metal semiconductor junctions, and we're going to be drawing an energy band diagram. So first thing we want to do is understand how to draw the energy band diagram of a metal. You have the Fermi level, and you have the free electron level. Notice that in the metal, we don't have EC, EV. We don't have the conduction band. We don't have the valence band, because those are not important to a metal's function. In the semiconductor, by contrast, remember we have the conduction band up here, the valence band down here, the Fermi level is in the middle. The distance between EF and EC, the distance between EF and EV, those are important parameters of a semiconductor. But in a metal, you only have a Fermi level. The metal is always conductive, whereas the semiconductor is conductive dependent on doping or temperature. The metal itself is always conductive. So we don't even bother drawing in any type of conduction band or valence band in here. That's usually one of the confusing points about drawing the energy band diagrams for metals. The metal energy band diagram is actually very simple. You just have a Fermi level and you have this free electron level. So if most of the electrons are right below the Fermi level, remember that below the Fermi level this band is full. Above the Fermi level this band is mostly empty. So most of the electrons are just below the Fermi level within this band. An electron attains enough energy, it will, if it attains an energy equal to Q times phi m, I'm sorry, it should be just phi m. Let me fix that. because phi m is given, the work function is given in terms of electron volts. If the electron gains an energy equal to phi m, it will go to the free electron level. At that point, it will be released from the material. That's called the photoelectric effect.
So you mean that there is, in metal, there is no valence band and conduction band difference, just a band?
That's correct. In metals, there's no conduction band, no valence band, just the Fermi level is within one band. And this band is always conductive. That's a key difference between metals and semiconductors. Because, in order to make something conductive, let's remember what we need. We need to have carriers, and we have to have empty states. So this band is half full here, so we have lots of carriers here, and we also have a lot of empty states, because above the Fermi level, this band is empty. So the metal is always conductive. Now looking on the right side of the diagram, so the semiconductor part of it. In the semiconductor, we have two bands, conduction band and the valence band, and we have the Fermi level somewhere in between there. Now the semiconductor also has a free electron level. We just haven't talked about it yet. If you blast a semiconductor with high energy light, an electron can also gain enough energy to go to the free electron level. Now the way the semiconductor work function is described is slightly different. It's defined as the distance between the Fermi level and E0. But like if you compare this to a metal, an electron will, most of the electrons are near just below the Fermi level here, so the electron would gain enough energy to go to the free electron level. In the semiconductor case, the definition is still the same. Phi s is the difference between EF and E0. However, in a semiconductor material, remember that there's a lot of the electrons. There aren't any electrons right at the Fermi level. The electrons are slightly higher than the Fermi level, near the conduction band. For that reason, we define another quantity called the electron affinity. And the electron affinity is given in terms of electron volts also. Just a quick correction here. This is often referred to as X sub S, the semiconductor electron affinity. Let's fix that. There you go. Okay. This should be X sub S. So the electron affinity for silicon is 4.05 electron volts. And you'll have that in your quizzes and exams and whatnot. So you'll have that constant with you. But it's something to remember. The band gap for silicon is 1.12 electron volts. You've probably memorized that by this point in the class. The electron affinity for silicon, meaning this X sub S, the difference in energy between the free electron level and the conduction band is about 4.05 electron volts for silicon. The work function for metals is something that you can look up. If you have aluminum, if you have silver, whatever metal you have, you can look up the work function in. It will be given to you on a test. The semiconductor work function, by contrast, is something that you have to calculate. Now, in a typical problem, I could give you X sub S, because X sub S is a constant for silicon, 4.05 electron volts. But the semiconductor work function, you can see it depends on the Fermi level. And the Fermi level moves depending on doping, right? So if I were to increase the doping of, let's say this is an N-type semiconductor. If I increase the doping of the N-type semiconductor, where's the Fermi level going to move? It'll move up towards the conduction band. So what happens to the semiconductor work function? It decreases. In a P-type semiconductor, it's the opposite. In a P-type semiconductor, when you increase the P-type doping, the Fermi level moves down, so the semiconductor work function increases. Okay, so that's something to keep in mind. All right, so now, yep.
So in the case of metal, the work function is just going to be the same as the electron affinity, but in the case of the semiconductor, it's not.
The question was, does the metal? Well, the metal doesn't have an electron affinity like a semiconductor does. Because the electron affinity is defined as the difference between the free electron level and the conduction band. Metal work function, we don't have EC. In the metal, we don't have EC and EV. So just EF, E0. Pretty simple band diagram for a metal. All right, so now let's look at what happens when we put an N-type Schottky, when we put an N-type material, N-type semiconductor, and metal together. And the key point here is, the key constraint here is that phi m is greater than phi s. Under this constraint, or under this condition rather, you'll end up forming an N-type Schottky barrier. This is a device that behaves very much like a diode. Now, if phi m is less than phi s, you're going to actually form an ohmic contact. That's what we'll talk about on the next slide. But this slide, we're forming a Schottky barrier. So we're just going to draw the energy band diagram step by step, just like we did with the PN junctions. Okay. So how you go about drawing these energy band diagrams is actually pretty straightforward. The first thing you do, you draw the semiconductor part of it. So in this case, we have a metal here and an N-type semiconductor on the right side. So the first thing we'll do is we'll just draw the semiconductor band diagram. And you should be quite comfortable about drawing the semiconductor band diagrams. We have a N-type semiconductor, so the Fermi level is above EI. Okay, and you can find the distance between EF and EI based on the doping. So this you know how to do. The next step is to draw E0. Okay, so this is something we haven't done before, but it's very easy to add to your band diagram. So you'll typically be given the electron affinity, the difference between EC and E0. That's 4.05 electron volts for silicon. And based on the location of the Fermi level, you can figure out phi s, the difference between EF and E0 in the semiconductor. Okay, so in your diagrams, you can also add an x sub s. That's the distance between E0 and EC. And that's a constant for silicon, 4.05 electron volts. So this portion of the band diagram, any questions on this part? Should be pretty easy to do. Now the next part, you draw the metal. Okay, now when you draw the metal energy band diagram, line up the Fermi level with the Fermi level of the N-type semiconductor. So just draw the Fermi levels like this as a straight line. Remember that at equilibrium, the Fermi level is a flat horizontal line. Doing it this way will help you line up the band diagrams and do the band bending in a relatively easy manner. The next step is you draw in the E0 for the metal. Because the metal has an E0, and the distance between those is given by the metal work function. That will be given to you in the problem. So you've drawn the two band diagrams independently now. Now, just like the PN junction, you have to connect those band diagrams together. Now, if you remember with the PN junction, we connected EC on one side to EC on the other side. We connected EV on one side to EV on the other side. We can't do that in a metal because we don't have EC and EV. So what we do have is, what they both have is a free electron level. So we match those up. And so what you do is you draw a connecting line between E0 and EV. We're going to go from here to here. So, and it goes up like this. You see, there's a discontinuity here. The difference between the metal semiconductor junction and a PN junction is that, remember, in a PN junction, it was more like, the connection looked more like this, right? But in a metal semiconductor junction, you only have half of this. Okay, so that's why it looks like just, just a half of an arc. In a PN junction, this arc would continue on the EC on the P side of the semiconductor. Okay, so again, you line up these two guys together line up the Fermi levels and just draw a connection between the two E0s. Next part is, if one of the bands has a bend in it, if E0 has a bend in it, so does EC, so does EI, and so do EV. Okay, so these lines are running, the spacing between these two lines run constant with each other. Okay, you can think about these as all like parallel lines. Okay, so whatever bending you have in this part of E0 is the same bending as you have in all these other bands. All right, so we've drawn the band diagram. Now, one point of note here is that in some of the simplified band diagrams, they don't draw the E0, they only draw the EC, EF, EI, EV. They only draw this bottom portion of the diagram. So just keep that in mind so you don't get confused if you're looking at other diagrams. Now, we have to analyze what's happening here. We have a metal on one side and an N-type semiconductor on the other side. In the N-type semiconductor, we're more concerned with what the electrons are doing. Because in an N-type semiconductor, we have a lot of electrons. We have very few holes. So if there's some type of electricity conduction happening in this device, it's going to be due to the electrons more than the holes. So again, we draw the electrons here. And you remember why I have this like triangular drawing, because there's a higher density of electrons near the conduction band. As you go further away, the electron concentration decreases the farther away you are from the Fermi level. So you have electrons built up, and this should look familiar by this time. This appears as a potential barrier. This potential barrier is going to prevent the electrons from going from right to left like this. This is very similar to a diode. It forms an energy barrier. And this energy barrier has a height, and the height of this energy barrier is the built-in potential of the Schottky barrier diode, just like the PN junction. Okay, so there's a lot of similar concepts here. This distance here in the band diagram is Q times V0. So let's say, for example, this distance here was like 0.6 electron volts. If I asked you what V0, the built-in potential was, you could say it's what did I say? If the distance here was 0.3 electron volts, then the built-in potential would be 0.3 volts. There's another feature in Schottky barriers, and that's called the barrier height. That's this distance here. It's the distance from the Fermi level on this side, to the top of this conduction band on the N side. And so the equations for these are quite simple. The QV0, this potential barrier, is equal to phi m minus phi s. Now the reason for this is pretty simple. You can just look at the band diagram. This is phi m. This is phi s. So this distance here is phi m minus phi s, right? The amount of bending in this portion of it, so this distance here is going to be equal to this distance here, because the amount of bending here is equal to the amount of bending here. So this QV0 is simply equal to the metal work function minus the semiconductor work function. And this barrier height is equal to the metal work function minus the electron affinity. The electron affinity, remember, is the spacing between E0 and EC on the semiconductor side. All right. Now, if you take this band diagram and you think about what happens in the forward bias, what's going to happen in the forward bias if we forward bias this device? Meaning, let's say we place a positive potential on the metal side. What's going to happen to the band diagram?
QV is going to reduce.
Absolutely. Yes, QV will decrease. Imagine that this side of the diagram, so when you apply a positive potential to the metal side and a negative potential to this side, then this side of the band diagram is going to go up. The Fermi level on the right side will go up, similar to a diode. And just like a diode, increasing the Fermi level on this side, if we were to shift this Fermi level up, we'd see that we'd end up reducing this barrier height. That makes it easier for the electrons to flow from right to left. And when they do flow right to left, look what happens. The electrons will come over to the metal side. If this barrier didn't exist, then the electrons could just go over to the metal side. And once they're over to the metal side, the metal is conductive, right? So the electrons will actually go to the energy states down here, which are free, or if these are mostly occupied, they'll basically go to a region close to the Fermi level, and there'll be a lot of empty states for them to go into. It'll be easy. The electrons, once they're in the metal, they can move back and forth very easily. Okay, but this barrier height is preventing the electrons from going onto this side. Now the hole side of the part of it, what are the holes doing? First of all, remember we don't have that many holes in an N-type semiconductor. But there are some limited number of holes here, or empty states here. Now the Fermi level here in the metal, you can imagine that below the Fermi level there are a whole bunch of states, but they're mostly full. Okay, so below the Fermi level there's not much interesting stuff going on. Okay, so that's why we're focusing on the movement of the electrons in the Schottky barrier. Okay, so you can obviously see from the fact that we have this energy barrier and the fact that the energy barrier reduces when we apply a forward bias to it, that this thing's going to behave very similar to a diode. The physical model also looks like a diode. It looks like a one-sided diode. So here are the things that sort of happen in this device. So electrons diffuse from the semiconductor to the surface of the metal and accumulate there. And recall that in a metal, charge accumulates on the surface, not within the metal. So the electrons have diffused from the semiconductor, from the N side to the metal. Now, when the electrons leave the N-type semiconductor, they leave behind a depletion region. We go back to our earlier concepts here. I want to relate this to what we talked about earlier in PN junction. In a PN junction, remember, electrons diffused from the right side to the left side, holes diffused from the left side to the right side. Okay, and when the electrons diffused away this way, they left behind a depletion region, positively charged ions, and those were the positively charged arsenic or phosphorus nuclei that had a positive charge associated with it. If you remember, it looks something like, where is it? It looked like this. The electrons diffused over here, they left behind these positively charged nuclei. These are the dopant ions. And the same thing happened with the p-type region. Now, if you have a metal semiconductor junction, this part, obviously, the left side doesn't happen because we don't have a p-type semiconductor here. We just have a metal. But what happens on the N side is actually quite similar. The electrons diffuse from right to left, except they diffuse onto the surface of the metal. Now, if you remember from physics, metals can hold charge at their surface. They usually don't have charge inside them. So all the electrons that diffuse from the semiconductor into the metal, they deposit themselves right on the surface of the metal. This diagram is a little confusing, I think, because it's sort of showing that the electrons have gone into the metal. That's not quite accurate. The electrons actually accumulate at the surface of the metal, right at the junction between the two materials. So this looks very much like a P plus N junction, because you have a large depletion region on the N side, but you really don't have a depletion region at all on the other side of the junction. Okay. Remember we said in a P plus N junction, the P plus side has a very, very small junction width, and the N side has a very wide junction width compared to the P side. This is exactly, very, very similar. So we have like kind of a half a depletion region here. The charge distribution and electric field resemble a P plus N junction. The electrons from the N side accumulate into a thin sheet of charge on the metal. Andrews?
Yeah, I'm a bit confused with the concept because if you have a metal, you expect it to have more electrons, right? If you have a metal, depending on the type of metal you have, if you have a metal that has like 2 valence electrons combined with an N-type semiconductor, whose maybe the doping level is not matched with the number of electrons the metal have, will you still have this kind of process going on where there's fusion of electrons from the N-type to the metal?
Oh, good question. You're saying why do electrons diffuse over to the metal if the metal already has a bunch of electrons? Okay, that's a good question. Let me think about that for a minute.
Could it be that the metals that they use have holes?
Wouldn't it just be the concentration gradient?
No, the reason for it Well, the metal actually has a high concentration of electrons. So Andrew's question is a very good one. Andrew's question was, why do the electrons diffuse from the semiconductor to the metal when the metal already has a very high concentration of electrons? We always say diffusion happens from high to low concentration, right? The answer to that question actually has to do with the energy band diagram. Now, I drew the energy band diagram at equilibrium, okay? But before equilibrium is established, if you imagine that this side of the diagram, let me just redraw it here. So let's say this is E0 for the metal. Sorry, let me clean this up a little bit. E0 for the metal. And this is EF. And then this is EF for the semiconductor. This is E0 for the semiconductor. So this is the metal, and this is the N-type semiconductor. Now, initially when the two materials are brought in contact with one another, the free electron levels will line up. And once equilibrium is established, the Fermi levels will line up. So this is the conduction band, and this is the valence band. Now, once equilibrium is established, the band diagram will look more like this, where you have the Fermi levels are lined up with each other. Not a great diagram, but you get it. You get the idea. Now, when you initially bring the two materials together, the E0 levels match up rather than the Fermi levels. You can see that the Fermi levels are at two different points at this point. Notice that the electrons here, the N-type material has a bunch of electrons in just above the conduction band. These electrons are actually at a higher energy on the N side than they are in the metal. So the electrons like to go from high energy state to low energy state. So these electrons are going to basically go like this, because remember, this is within a band. Okay, and below the Fermi level, most of those states are full, but above it, there's a lot of empty states there. So the electrons could actually just fall into one of these empty states here. And they would prefer to do that because they're at lower energies. Now, as those electrons start dumping over, the depletion region starts to form, the Fermi levels come together, they line up with each other, and then you form this barrier which prevents further diffusion. So that's sort of the energy band explanation of what's going on there. Once this depletion region is formed, once this equilibrium is established, it looks very much like a PN junction. So remember that if you have a slope in the band diagram, whenever you have a slope in the band diagram, that tells us that we have an electric field. Right? There's going to be an electric field that's pointed. Which way is the electric field going to be pointed here? You can just look at the amount of charge from right to left. Electric field always points from the positive charges to the negative charges. So the direction of the electric field is also the same as a PN junction. If I were to ask you to find the width of the depletion region here, you can do that using the same formulas, the capacitance and depletion layer widths, using the same formulas that were derived earlier for a P plus N junction. Okay, so you could just assume that NA is much larger than ND. Those formulas for capacitance and depletion width, they simplify. And those are the formulas that you could use for finding the width of a Schottky barrier. Schottky barrier and forward and reverse bias. We talked about this a little bit, but this is what the diagrams look like. If you place the Schottky barrier in forward bias, the Fermi level on the semiconductor side is higher than the Fermi level on the metal side. You've applied a positive potential on the metal side, a negative potential on the semiconductor side. that causes the barrier height to reduce. So it used to be QV0, and now it's reduced to, now it's reduced to Q times V0 minus V. By reducing the barrier height, the electrons more easily can come over to this side, so you get a large increase in the current. This diagram also shows what's happening at the bottom of the diagram. Below the valence band, most of these states are full, and below the Fermi level in the metal, most of the states are full. So more of the interesting things are happening here in the energy band diagram. Now reverse bias does the same, does the opposite. Again, very similar to a diode. When you place it in reverse bias, you're increasing this barrier height, further limiting the ability of electrons to go from this side to this side. So as a result, what do you think will happen to the current? What kind of currents do you think you'll get in the reverse bias? Take a guess.
When they tunnel over, tunnel through because the bands are so close together.
Tunneling can actually happen in a Schottky barrier. We'll get to that a little bit later. But the basic concept would be that because the barrier height is so large, there will be no reverse current, just like a regular diode. So in the reverse bias, the Schottky barrier does not conduct current. Now imagine if you're in a lab, right, and you put your metal, you take a metal lead or a metal wire and you put it to a semiconductor, and you expect to be able to get current through there. And because of the Schottky barrier, if you reverse bias the Schottky barrier, you don't get any current at all. You think your semiconductor device is not working. So that can be a big pain, right? So in a lot of cases, when we're trying to make contacts to the metal, we want to avoid making a Schottky barrier. Instead, we want to make an ohmic junction. We'll get to why, we'll get to how to make an ohmic junction in the next few slides. But the condition for a Schottky barrier is if the metal work function is greater than the semiconductor work function, you will get a Schottky barrier. All right, so moving on then. So the question is, how is this different from a PN junction? I've mentioned all these similarities. There's one big difference from a PN junction. Holes. Yeah, exactly. In this N-type Schottky barrier, we have a metal and an N-type semiconductor junction. The electrons are pretty much doing everything here. The electrons are responsible for, electricity going through the Schottky barrier. So there's no holes involved. That's one of the big differences. What else can I go over? Another things you can interpret from looking at this band diagram. So we have this barrier here, and when the barrier reduces, the electrons can dump over to this side. Okay. However, can the electrons go in the opposite direction? Look at the device in forward bias. In forward bias, you've reduced this potential barrier so the electrons can go from here. An electron here could find some empty states here, so the electron just drops down here. Can it go in the opposite direction? I heard yes and no. Oh, I'm talking about the forward bias right now. So in the forward bias, we've reduced this barrier height so the electron says, oh, hey, I see an empty state near me, and it's way down here in energy. I would prefer to go to the lower energy state. So the electron will just hop down here. That's how you get conduction in the forward bias. Why doesn't it go in the opposite direction?
They want to be in the lowest energy state possible.
Yeah, they want to be in the lowest energy state possible. There's a barrier height here. Okay. So this is another sort of difference between the PN junction and the Schottky barrier. The electrons can move this way, but the barrier height, phi m minus the electron affinity, will prevent the electrons from going in the opposite direction.
that mean there's no drift current?
I'm sorry?
Does that mean there's no drift current?
There's very little drift current. Yeah, yeah, exactly. Going to the valence band?
Yep, from the metal.
Okay, from the metal.
To the valence band.
Going from the metal to the valence band. Okay, so from the remember the valence band is mostly full because there aren't that many empty states there. So these are all full. These are all full. So because everything's full, there's no room for carriers to move around. So most of the interesting things are happening up here. Okay. Now moving on, the Schottky barrier IV curve looks something like this. In the forward bias, you get this exponential IV characteristic. In the reverse bias, you just have a small negative current. The equation, it looks the same as the diode. I is equal to the saturation current times e to the QV over KT minus 1. Basically, that describes this equation. The difference is that the I0, there's a slightly different formula for the I0. I'm not putting it here. I'm not putting a derivation in here how to find I0. But qualitatively, you can understand that it's exponentially related to the barrier height, phi b. So the barrier height meaning this height right here, which is equal to the metal work function minus the electron affinity, e to the negative q phi b divided by kt. Inversely related to the exponential of the barrier voltage. Okay, so Schottky barrier is very similar to a diode. Now you can also make a Schottky barrier with a p-type semiconductor combined with a metal. If the semiconductor work function is greater than the metal work function. Okay, so it's the opposite condition as compared to the n-type semiconductor. If the semiconductor function for the p-type is greater than the work function of the metal, then the band diagram will look something like this. So let's take a closer look here at what's happening here. This is the band diagram where the metal and the semiconductor are just placed next to each other for illustrative purposes. In the metal side, we just draw the Fermi level, and up here is the free electron level. This is E0. It's not labeled, but we can just call that E0. And this is the metal work function. In the semiconductor side, you have the conduction band and the valence band here, and you have the semiconductor work function there. And when the two Fermi levels meet up with each other, the band bending looks like this. It goes in the opposite direction. It bends down instead of up. Now, in a p-type semiconductor, we're looking at what the holes are doing. The holes encounter an energy barrier here that prevents them from going into the metal side of the junction. So that gives you the built-in potential for the junction on that side. So this region here, where there's a slope in the curve, that is the depletion region. The metal semiconductor depletion region looks something like this, where there's positive charges on the metal side and a negatively charged depletion region on the semiconductor side. So I would encourage you to draw out these energy band diagrams for the p-type Schottky barrier on your own, just like we did with the n-type, step by step, so that you're comfortable with how to do this. And also, we'll have some problems on these types of things in the homework set. Next, ohmic junctions. As I mentioned, like if you put a metal on a semiconductor, suppose in some cases maybe you want a diode-like characteristic, but in a lot of cases when we're just testing semiconductors, we would like to have an ohmic junction. When we make a contact to the semiconductor, we would like to have a linear IV characteristic rather than this nonlinear barrier type relationship where we only allow current in one direction. So this is the IV characteristic for a diode and a Schottky barrier. This is the IV characteristic for an ohmic junction. So you'll notice that this looks like it's just the IV characteristic for a resistor, right? So let's say these were two IV characteristics. This is one line, and this is the next line. Which is a better ohmic junction of these two lines? These are both IV characteristics.
That's not so steep.
The one, do we want it steeper or less steep?
Less steep.
Well, think about this for a second. If we want to make a contact to a semiconductor, do we want a lot of resistance or do we want little resistance? We want low resistance. If we make contact to a semiconductor, we usually want to minimize the resistance. So which one of these lines has less resistance? The more steeper one, right? If there's less resistance, it'll give you more current for a specific amount of voltage. So remember that Ohm's law V equals IR. Now this is plotting I versus V rather than V versus I. So oops, V equals IR. So if we put I in terms of V, it's going to be 1 over R times V. So this is this Y equals MX plus B form. So the slope of a line, if we're plotting current versus voltage, the slope of this line is equal to 1 over the resistance. So the line which has a steeper slope has less resistance. Larger slope will have less resistance. Okay, so a lot of situations we would like to have an ohmic junction, and ideally we'd like it to have a low resistance contact. But let's talk about how we can make an ohmic junction. There's two ways to make an ohmic junction. First of all, you can choose the work functions opposite the Schottky type. For example, for an N-type ohmic junction, you could choose phi m as less than phi s. For a P-type, you can choose phi s as less than phi m. The other way to make it is to just do what's called a tunneling junction. If you dope the semiconductor side very high, we can get tunneling. As Michael was saying earlier, there's a tunneling effect that can happen in metal semiconductor junctions. So let's look at the band diagrams for an N-type ohmic junction. In the N-type Schottky barrier, phi m was greater than phi s. That was the key thing. If phi m is less than phi s, then we'll get an ohmic junction. And this is what the band diagram for an ohmic junction looks like. So this is the band diagram for the metal. This is the band diagram for the semiconductor. You can see the semiconductor work function and the electron affinity there. Now, what happens here, you can imagine when the Fermi levels line up. So if we move this Fermi level up, if you imagine moving this up, then what's going to happen is that E0 is going to move up as well, and you'll have these lines will bend down instead of bending up. And the band diagram will look like this. Okay, you have your Fermi level here, the E0 line bends down, the EV line, I'm sorry, this is EC, and this is EV. Now this is exactly the opposite of a Schottky barrier. In the Schottky barrier, this line was going up like this. Okay, that was creating an energy barrier. Now this line is kind of coming down like this. So if you were to have an electron, if you have a bunch of electrons in here, this region, let's draw this. Oops. So if you were to have a bunch of electrons up here, just like before, they don't have that barrier that's preventing them from moving to the metal side. So these electrons can just go straight through like this. Okay, and because the barrier height is not that much, this is usually a relatively small distance. The electrons can go in the opposite direction as well. So they can go back and forth more or less freely. This little change in the barrier accounts for, it may add a little bit of resistance to it. In other words, you may need to apply a little bit of a voltage in order to get electrons to flow from the metal to the semiconductor. From the semiconductor to the metal, they'll flow very easily. The point is this barrier is relatively small, so the electrons generally have the ability to move back and forth. So this is what you want. This is what you want in a nice contact. So as a result, the ohmic junction will have an IV characteristic that looks more like this rather than like the Schottky barrier. So a p-type ohmic junction can be made if you have a metal in a p-type junction with phi s is less than phi m. This is what the diagram looks like. Notice that we have this barrier on the n side, but we don't care about that because in a p-type semiconductor, we're more concerned with what's going on down here. All right, the holes that are on the p side of the junction, remember holes like to go up the slope. Okay, so the holes can easily go into the semiconductor region. Okay, so in this case, the hole movement back and forth is what's responsible for conducting electricity back and forth in the ohmic junction. The final type of ohmic junction, first of all, to give you a little bit of why we'd want to have tunneling type junctions. To create n-type and p-type ohmic junctions, you have to make sure that these constraints are met. The metal work function is less than the semiconductor work function, and in the case of the p-type, semiconductor function is less than the metal work function. Now, sometimes it's hard for us to, we can't always just add a different metal into our semiconductor process. Let's say we're working with copper, right? And we can't just change out the metal for a different one with a different work function without significantly changing the expenses and the infrastructure required to work with a new type of metal, right? And also, we can't easily just change the semiconductor doping because the semiconductor doping controls a lot of things too. You found out it controls the resistance of a semiconductor resistor. In the case of a diode, it controls the saturation current, and so on. So, if you go for these types of ohmic junctions, you have to tune the phi s and the phi m. That can be a pain to do. Another way that you can get ohmic junctions regardless of the semiconductor and metal work functions is to just dope the semiconductor very highly. If you put a metal in contact with a very highly doped semiconductor, you'll get an ohmic contact virtually always. And that's the trick. That's the easy way to do it. This is why we'll talk about when we make contacts into the wafer. So if this is what a diode looks like, you have the P plus regions, N plus regions. Those are the regions where the metals will bond to the semiconductor. This always forms a good ohmic contact. Why does it do that? Well, these are called tunneling type contacts. If you have moderate doping, let's say you have an N-type Schottky barrier, okay? So we've already seen what this looks like. There's a barrier here like this that prevents an electron from going back and forth between the two sides. If you were to dramatically increase the doping and dope this N side very, very highly, then the band diagram will actually look something like this. The depletion width will be more narrow. If you remember with diodes, there was this, from the diode chapter, you remember that the higher you dope the diode, the smaller the depletion widths. Well, if you dope an N-type semiconductor very highly, the depletion width, remember the region where there's a slope here, that's the depletion region. This is moderate doping, so it has a relatively wide depletion region. And if you have a very high doping, you have a very narrow depletion region. When you have a very narrow region like this, even if there's a tall energy barrier, if it's very narrow, the electron can tunnel through it. The probability of an electron tunneling through that barrier is exponentially related to the width of the junction. So when you have very narrow widths, the probability that an electron will tunnel through there goes up exponentially. So just by highly doping the semiconductor region, so you get your band diagram that looks like this, we can get ohmic junctions that work on the basis of tunneling. Now, another thing that will happen, which it has less to do with tunneling, but remember that if you have an N-type barrier, then if you have an N-type material, the higher you dope it, EF will become closer to EC. So this level here will become even lower, and that will allow current to flow in the opposite direction. Okay, also by tunneling. You'll still have this barrier, but electrons will be able to go both ways. They'll be able to tunnel through that barrier both in both directions. This is what an actual diode looks like. So sort of summing up this module. The example below shows a p-type silicon wafer with a patterned N region. So the N plus and the P plus regions, which are also formed using diffusion, are added to form ohmic contacts to the N and P regions of the semiconductor. If we just put the metal on the p-type portion of it, and we just put the metal on the n-type, well, let's back up for a second. What are we trying to do? We want to make a diode, and we want to have metal contacts into the p and the n sides. So, our first, the most simplest approach would be to just put the metal right on the p-type wafer, and put the metal right on the n-type region. Turns out that may not work in all circumstances because you may form Schottky barriers at those junctions. The way you avoid that is by creating this P plus region. Okay, this forms a tunneling contact between the metal and the semiconductor, and the same thing happens here. So this gives you a nice contact into the N region, a nice contact into the P region, and then you form, this interface between the P-type material and the N-type material. That is your diode. That's where the depletion region forms. That's where all the interesting physics happens. And if you were to connect this to a voltage source, you would get that IV characteristic that we're talking about. So this is a little bit different than the diode that you looked at in class. This is a lateral diode where the P-type and the N-type region, they're sort of, the current flows kind of in this direction. The one that you looked at in the lab was a substrate diode, where you have the N region on top, and the P-type region, you just form a contact on the P-type region at the bottom like this. Okay? Same idea, though. Any questions? All right. Good. Then to sum up, the metal semiconductor junction portion of this, what I would like you to do to study for this, there would be one question on the homework. It's really, it's a relatively easy one, similar to what we did in class today. I would like you to be able to fill out this chart or go through each one of these combinations. So you have an N-type material, phi m is less than phi s. What type of junction will you form, ohmic or Schottky? Be able to draw the energy band diagram for it and be able to explain some of the physics of how that works. Same thing for all these other combinations. So you have 6 different combinations. Figuring out whether it's ohmic or Schottky obviously is very easy. You've seen it in the notes. But just be comfortable drawing the energy band diagrams for these different combinations. The one that we did today in class will seem very easy because we did it together, but just do it on your own. Draw the band diagrams on your own just to make sure that you know how to do this. So I imagine we'll have a test question on something like this. For the highly doped semiconductors, be able to draw the energy band diagram so you can see the tunneling, the fact that you have a narrow barrier which can allow tunneling. All right, summary of this chapter. We talked about PN junctions, we talked about metal semiconductor junctions, and with PN junctions there were 3 states. There's the equilibrium, there's forward bias and reverse bias. These 3 states obviously apply to metal semiconductor junctions as well. In each one of the states, you should understand the energy band diagram, the physics of the depletion region, carrier concentrations, what the carriers are doing, and then the drift and diffusion currents that occur, and also the recombination, generation and recombination that occurs in each one of these different states. So in metal semiconductor junctions, they can behave as a diode or a resistor, depending on phi m and phi s. So just understand the energy band diagrams, how to draw them, how they're similar to a diode, how they're similar to a resistor, depending on what type of junction you have. So, any questions on metal semiconductor junctions? All right, good. So let's. We could just take a. Just take a 1 or 2 minute stretch break. I'd like to go on to the MOSFET chapter after this.